Assalamualaikum girls. I am Shamsunisa from Royal Degree College, Chemistry Department. As we all know that we are dealing with Unit 4, General Chemistry. Today we'll study Chapter 3rd, that is Infrared Spectroscopy. In this, we'll talk about different regions of infrared radiation in the electromagnetic spectrum, modes of vibration of diatomic and polyatomic molecules, selection rules for infrared absorption, active and forbidden vibrations, fingerprint region, and interpretation of spectra, alkanes, aromatic, hydrocarbons, alcohols, carbonyl compounds, and amines. First, we'll study about different regions of infrared radiation in the electromagnetic spectrum. Infrared radiation broadly refers to that part of the electromagnetic spectrum that lies between the visible and microwave regions. Mu bar, it is equal to 200 to 13,000 per centimeter. This limited part between 4,000 and 200 per centimeter in the electromagnetic spectrum is of great practical importance for understanding and identifying organic compounds. Infrared region is generally divided into three regions, namely near infrared region, normal infrared region, and far infrared region. The region between 4,000 to 13,000 per centimeter is called near infrared region. The region between 700 to 200 per centimeter is called far infrared region. Far infrared region in infrared spectroscopy is called fingerprint region. Many organic compounds absorbs infrared radiation and exhibit vibrational and rotational changes in the molecules of the organic compounds. Infrared spectroscopy is called vibration rotation spectroscopy. Now we'll see about modes of vibration of diatomic and polyatomic molecules. At ordinary temperature, organic molecules possess constant state of vibration. There are two types of molecular vibrations. These are, first type is stretching. You can see the figure here. And second one is bending, which is also named as deformation. Here you can see the structure of bending or deformation. First of all, we'll talk about stretching vibration. A rhythmical movement along the bond axis is stretching. In this, the interatomic distance may increase or decrease. Here you can see the figures. It is showing the increase in the interatomic distance, isn't it? In the second figure, this is the normal one. And another one, if you see the third figure, here the interatomic distance decreases. Second type is bending or deformation vibration. This consists of a change in the bond angle between the bonds bound to the common atom or the movement of a group of atoms with respect to the remainder of the molecule without movement of atoms in the group with respect to one another. So the molecules exhibit different modes or types of motion with respect to the molecule or with respect to the atoms forming the bonds. Each molecule exhibits three types of motion. These are, first type is translational motion, second one is vibrational motion, and the third one is rotational motion. So the total number of these modes of motions is 3n, where n is called the number of atoms in the molecules. Out of these 3n modes of motion, translational 3, rotational 3 or 2, that is nonlinear 3, linear 2. Vibrational 3n minus 6, nonlinear, and 3n minus 5, linear. For a diatomic molecule, Total number of modes of motions is 3 into 2. So as we are using the formula 3n, n is here, the number is 2. So 3 into 2, we will get the value 6. Out of these, rotational 2, translational 3, and vibrational 1. Now for a 3 atom non-linear molecule, total mode is 3 into 3. So it is equal to 9. Here translational 3, rotational 3, and vibrational 3. These vibrations are generally classified into two types. These are stretching and bending. Stretching is again of two types. First one is symmetric stretching. Here you can see the stretching is same in the same direction, symmetric. And second one is asymmetric stretching. Here you can see the figure, the stretching is in the opposite direction. They are not same. So asymmetric. Bending or deformation modes are of four types. These are in plane bending 2 and out of plane bending 2. These four are named as, first one is scissoring. Here you can see the figure. Second one is rocking. Third one is twisting, and the fourth one is bending. All these are the modes of vibration of a 3 atomic species. Each of the vibrational modes may give rise to an absorption band. Vibrations generally follow Hooke's law, that is simple harmonic motion. This can be written as V by C, it is equal to mu bar. Its value is equal to 1 by 2 pi C under root K by mu, where K is called bond strength, mu is the reduced mass of the bonded mass, and mu, its value is equal to m1 into m2. m1 is what? Mass of one atom into mass of second atom divided by mass of one atom plus mass of second atom. The frequency of vibration corresponding to V0 minus V1 or V0 to V1, that one is called fundamental frequency, indicated with V0. So here we are using this formula, vibrational energy EV, it is equal to V plus half into h mu, where V is called vibrational quantum number. Its value will be 0, 1, 2, 3 and so on. And h is called the Planck's constant, and mu is nothing but frequency. Next we'll see selection rules for infrared absorption, active and forbidden vibrations. Infrared light is absorbed by a molecule if it is a dipole, or if dipole character occurs to the molecule on infrared absorption, that is oscillatory dipole. Hence, quantum mechanical selection rules are arrived at for absorption of infrared radiations by molecules. These are, first one is vibrations which are not centrosymmetric are active, and second type is permanent dipole or oscillatory dipoles, only absorbs the infrared radiations. Most organic molecules satisfy these two conditions. Hence, infrared spectra are most useful and most informative for organic molecules. The intensity of an infrared band or peak depends on the difference between the dipole moment of the molecule or a bond in the ground state and in the vibrational excited state. Greater the difference, greater is the intensity. If a particular vibration is not influenced by any structural change, at that time the frequency V0 usually corresponds to the fundamental frequency arrived at by using Hooke's law. The frequency depends on the bond strength K and reduced mass mu of the atom of the bond. So electronic effects also affect the frequency. Transitions from the ground state, that is V equal to 0, to the first excited vibrational level, that is V is equal to 1, absorbs strongly and gives intense band called fundamental band. That is V0 minus V1. Okay, V0 to V1 we can say. That is from ground state transitions will be up to the excited state. That is the first excited state. Therefore, delta E vibration, that is the change in vibrational energy, it is equal to vibrational energy in the first excited state minus vibrational energy in the ground state. So we are subtracting. So vibrational energy EV, it is equal to V plus half H mu. It is the formula which we are using here. So change in the vibrational energy, it is equal to, what is the value of EV? That is the energy of vibration. That is V. V, here the value of V is 1. That is the first excited plus half into H mu. Then minus another vibration energy which is in the ground state. That is V, here value is 0 plus half into H mu. So in the next step, what we are doing, see here, look at this. 2 into 1, you will get 2, plus 1, 3. Okay, 3 by 2, H mu. Then minus 0 plus half, you will get half. So 1 by 2, H mu. H mu is common, so we are taking H mu as common in the next step. Now we can write 3 by 2 minus 1 by 2. So the bases are here, the denominators are same, which is present in the base, isn't it? They are same. So we are writing the 2 as it is. Then 3 minus 1, we will get 2. So 2 by 2, 2 ones are 2. You will get the value 1. So delta H vibration, that is the change in vibrational energy, it is equal to H mu. Now other absorptions are V0 to V2. Okay. So here, therefore, delta E vibration, it is equal to vibrational energy V equal to 2 minus vibrational energy V equal to 0. Now the same formula we are using here. Vibrational energy EV, it is equal to V plus half into H mu. Okay. So here the change in vibrational energy, it is equal to energy in the second excited state minus energy in the ground state, that we are writing here. So delta E vibration, it is equal to 2. That is the value of V here, second excited state. Now plus half H mu minus 0 plus 1 by 2 H mu. Okay. So in the next step, 2 into 2, 2 2s are 4 plus 1 by 2. Okay. H mu, then minus 0 plus half, you will get half H mu. Then in the next step, we are adding this value. 4 plus 1, 5. First of all, what we are doing, we are taking H mu as common. Okay. Then we are adding this 2. That is 4 plus 1, you will get 5. 5 by 2 minus 1 by 2. Now, the denominators are same. So, we are taking 2 as common. Then 5 minus 1, you will get 4. 2 ones are 2, 2 twos are 4. So, you will get the value 2 H mu. That is the change in vibration energy. Now, in the next case, V0. See here, the transition is from ground state to the third excited state. Okay, V0 to V3. Same formula we are using here. Therefore, change in vibration energy, it is equal to vibration energy in the third state minus vibration energy in the ground state. Then we are using the same formula here, delta E vibration, it is equal to energy in the third state minus energy in the ground state, that is 0. So we are copying here 3 in place of V. 3 plus half H mu minus 0 plus half H mu. So in the next step, 3 2s are 6 plus 1 1s are 1. So divided by 2 H mu, then minus 0 plus half is half H mu. Then the H mu common, na? So we are taking H mu as common. 6 plus 1 7, 7 by 2 minus 1 by 2. As it is, here the bases are same, so we are copying the same, that is 2. 7 minus 1, you will get 6. 2 ones are 2, 2 threes are 6. So ultimately you will get the value as 3 H mu. That is the value of delta E vibration. That is change in vibration energy. It is equal to 3 H mu. So change in vibration energy, it is equal to 2 H mu. For the other case, change in vibration energy is equal to 3 H mu. These two are called overtones. So here we can say the transition from V0 to V1, that is called fundamental. Its value is equal to H mu. Then the transition from V0 to V2, that is named as first overtone. Its value is 2H mu. So the transition is from V0 to V3, second overtone. It is equal to 3H mu. Now we will see about fingerprint region. Its region will be in between, that is its range is 1500 to 700 per centimeter. The infrared spectra recorded in the region 4000 to 1600 per centimeter in the same solvent and under same conditions may be same for two identical compounds. But we cannot distinguish one compound from the other from these spectra. We only know about the nature, that is whether it is aliphatic, aromatic, heterocyclic, and also the functional groups present in them. But using the region between 1500 to 700 per centimeter, that region is called fingerprint region. We can identify the actual compound from the characteristic C single bond C, C single bond O, and C single bond N bonds in these compounds. This region is again subdivided into three regions. First region is ranging from 1500 to 1350. Second region is 1350 to 1000. And the third region is below 1000 per centimeter. These give more information about an individual compound. In any organic compounds, generally, stretching frequencies are mainly used. The bonds that are important are those due to C dash H, C double bond C, C double bond O, O dash H, N dash H, and C single bond N. As well as C here, C single bond C bonds are not very important. Why? Because of their high strength. C single bond C bond, it is showing the high strength. Because of that reason, it is not very important. 5 regions are important for examination of an infrared spectrum. These are, the first region is 3660 to 3200 per centimeter. Second region is 3200 to 3000 per centimeter. Third region ranges between 3000 to 2590 per centimeter. Then the fourth region ranges between 2500 to 2200 per centimeter. And the fifth region range is 1900 to 1650 per centimeter. Below 1500 per centimeter region is useful in knowing the substitution in the benzene ring, mono substitution at 300 to 730 per centimeter, di substitution at 850 to 700 per centimeter. Thus, approximately 4000 to 1500 per centimeter is functional group identification region, and 1500 to 667 per centimeter is the fingerprint region. The vibrations are generally fundamental, that is 0 level vibrations to first level vibration. Here you can see V0 to V1 vibration. But transitions from vibrational level 0 to level 2 and from level 0 to level 3 are also allowed, that is V0 transition to V2 and V0 to V3. These two are called first overtone and second overtone of the fundamental and ground level frequency, that is V0. The frequencies will be 2 or 3 times of V0. The first region, that is ranges from 3600 to 3200 per centimeter, gives O single bond H, and second gives the preference, or we can say the second gives the presence of OH, NH2 and NH, and as well as aromatic compound, that group. So here 3200 to 3000 per centimeter region gives CH frequency. 3000 to 2500 per centimeter region gives CN group. Then 2300 to 2100 per centimeter region gives C triple bond C and C triple bond N groups. 1900 to 1650 per centimeter region gives C double bond O group. Next, we will see about interpretation of spectra, alkanes, aromatic hydrocarbons, alcohols, carbonyl compounds, and amines. We'll start with alkanes. The stretching and bending, that is deformations, frequencies of C single bond H bonds are generally used in the identification of alkanes. The C single bond C bending frequencies occur at very low frequencies, below 500 per centimeter. These are weak. The C single bond C stretching frequencies are also weak, and they occur in the region 1200 to 800 per centimeter. C-H frequencies, stretching and bending of CH3 and CH2 groups are nearly constant in hydrocarbons. But the attachment of heteroatoms or carbonyl groups or aromatic rings may result in appreciable shift of C single bond H vibrations. Commonly, two C-H stretch bands or stretching bands appear below 3000 per centimeter, one for symmetrical and one for asymmetrical vibrations. C single bond H bending vibrations appear in the region 1485 to 1340 per centimeter. C single bond C bands are weak and less characteristic. These appear in the region between 1300 to 800 per centimeter. The group of bands corresponding to C single bond H bending of alkyl groups are characteristic. Example, 3-methyl pentane gives typical infrared spectrum. Now we'll study about aromatic hydrocarbons. Benzene has in it C single bond H, C double bond C, and C single bond C bonds. C single bond H stretching occurs in the region between 3050 to 3000 per centimeter. C double bond C stretching occurs at 1650 to 1450 per centimeter, and C single bond H bending, that is deformation, occurs at 900 to 700 per centimeter. C double bond C stretching is highly characteristic if there is no absorption at 1600 per centimeter, 1580 per centimeter, 1500 per centimeter, and 1450 per centimeter. It is a definite proof that the molecule is not aromatic. Monosubstituted benzene are identified by bands at 710 to 690 per centimeter and 770 to 730 per centimeter. Disubstituted, that is meta compounds, show two bands. One band is at 710 to 690 per centimeter and the another band is at 800 to 750 per centimeter. Ortho para shows at 770 to 735 per centimeter and 840 to 800 per centimeter respectively. Now we will study about alcohols. Alcohols show hydrogen bonding due to the presence of OH group. Hence, infrared spectra of alcohols are recorded in dilute solutions in non-associative solvents such as carbon tetrachloride. A sharp band appears in the region 3700 to 3500 per centimeter. The band is of high intensity and hence can be easily recognized. In polar solvents, hydrogen bonded alcohols, O-H bands occurs at low or lower frequencies. Generally, OH bands and C-O bands couple with each other in alcohol. Here you can see the structure. Single bond C, here one single bond hydrogen, and single bond OH. Hence, bands for primary, secondary and tertiary alcohols show some differences in OH bands. Primary alcohols, strong band near 1050 per centimeter. For secondary alcohols, near 1100 per centimeter. Tertiary alcohols, near 1200 per centimeter, and at 1410 to 1310 per centimeter. Two bands you can see here. So strong bands between 1250 to 1000 per centimeter are characteristic of C single bond OH frequency range, and the intensity decreases in the order primary showing more intensity compared to secondary, secondary showing more intensity compared to tertiary. It means that tertiary is showing the least intensity and the primary showing the more intensity. The band between 3700 to 3500 per centimeter due to OH is of primary importance in alcohols. Example, ethanol and benzyl alcohol gives typical spectra. Next we will deal with carbonyl compounds. Between 1650 to 1950 per centimeter, a strong band appears due to C double bond O group. But the frequency depends on the force constant, that is K, in the Hooke's equation. The force constant depends on inductive effect, conjugation effect, and steric effect present in the molecules. Positive inductive effect is high in ketones compared to aldehydes. So aldehydes absorb at higher frequencies than ketones. Here we can see the examples. HCHO, formaldehyde. Its range is 1750 per centimeter. CH3CHO, acetaldehyde. Its range is 1745 per centimeter. CH3COCH3, it is nothing but acetone. Its range is 1718 per centimeter. So carbon single bond hydrogen stretching frequency also distinguishes aldehydes from ketones. Aldehydes show C-H frequencies at 2820 per centimeter and 2720 per centimeter. Generally, conjugation effect dominates over inductive effect. The frequency decreases if conjugation is there. In cyclic ketones, C double bond O group frequency increases as the ring size decreases. Cyclopropanone, its range is 1858 per centimeter, cyclobutanone 1788 per centimeter, and cyclopentanone 1746 per centimeter. Aldehydes and ketones shows also keto-enol tautomerism. The keto-enol forms are distinguished by what is called keto-enol tautomerism, that is from the keto group converted to enol group, and enol group again converted back to the keto group. So the keto-enol forms are distinguished by the OH frequency, O single bond H frequency. So aliphatic aldehydes absorbs at 1740 to 1720 per centimeter. Negative inductive effect or negative inductive effect group increase the frequency. Here you can see the example. Acetaldehydes absorbs at 1730 per centimeter and trichloroacetaldehyde absorb at 1768 per centimeter. At last, we are talking about amines. These exhibit spectra due to absorption of N-H bonds. N-H stretching occurs in the range 3500 to 3300 per centimeter. The position depends on the hydrogen bond. Primary amines show two sharp bands. Secondary amine shows only one band, and tertiary amines do not show N-H bands. N-H stretching frequencies of aryl amines are higher than those of alkyl amines. Aliphatic amines are more sensitive to hydrogen bonding than aromatic amines. C-N vibrations for aliphatic amines are weak but appears at 1410 per centimeter and 1220 to 1020 per centimeter. With this, we have completed our chapter 3rd of 4th unit. Thank you for listening my lecture.